Hello. So we are now ready to start. And again, I apologize for the delay. So let's get going. So first, I want to review the sandwich theorem that we discussed at the end of last lesson. So we take functions that are defined on, let me highlight like this, defined on a domain that looks like this. So it's an open interval with one point removed. And when we make a graph of a function like that, we often write an empty circle like this to show that the function is not defined at that point. But even if it is not defined at that point, it may have a limit. And this theorem tells us about that limit for a function f of x, which we know is sandwiched between two other functions, g and h. So gx is less than fx is less than hx for all x in the domain, which is this red thing, and we write it, the open interval AB, with the point C removed. And if we assume that the limits of G and H both exist and are equal to some number L, then the sandwich theorem tells us that the limit of f of x also exists and it equals L. So we'll give some examples of this. I just wanted to remark, note at the bottom, that we stated this theorem last time with strict inequalities, so less than. And it also works with less than or equals. So the assumption less than is a stronger assumption, but we can weaken that assumption. Just use less than or equals here. So in particular, that's the way it's written in the book. So I wanted to make that note so you're not confused. Okay, I hope this becomes clearer with some examples. And actually using this theorem to calculate limits that we might not find it easy to calculate otherwise. So let's first say what a limit is, just in words. Just remind ourselves what we're talking about. Well, let's look at this function sine theta, function of theta. The domain is the whole of the real numbers. We can also use a smaller domain near zero. So that's what we do to apply this theorem. And then I ask, what is the limit of sine theta as theta goes to zero? So remember, the limit of the function is some value that as the variable theta gets closer and closer to some, for instance, 0, then the value gets closer and closer to something, the limit. That's vague, but we'll explain that precisely this lesson. But just by that vague explanation, if theta gets closer and closer to 0, you can see from the graph that sine theta gets closer and closer to 0. So you expect that the limit of sine theta is 0 as theta approaches 0. But how to prove it? Well, one way is using the sandwich theorem. And I give the argument here and a picture that shows you how the sandwich theorem is used. Because sine theta can be sandwiched between the graph absolute value of theta, so that's this V graph, and minus absolute value of theta. That's an upside down V. So for any theta, we have this inequality, that sine theta is between these two functions, the absolute value and the minus absolute value. And the limit of those functions as theta goes to 0 is just 0. So this is easier to prove than the limit of sine theta because, at least for positive theta, this function is just equal to theta. Okay, so I just want to make a note. So how to actually apply what we wrote on the last slide. So the theorem goes, for instance, we can apply the theorem on the domain -1 to 1 with 0 removed. So let me draw that in here. -1 to 1 with 0 removed like that. So that's one example of how a function sine theta can be sandwiched between two other functions. So another example. So if we have the limit of sine theta, we also ask for the limit of cos theta. And in the same way we can calculate it. A little trick to make it easier, that 1 minus cos theta is certainly positive because the range of cos theta is between -1 and 1. So 1 minus cos theta is positive. This part. And 1 minus cos theta, this is not obvious, but you can believe it from this graph, is less than the absolute value of theta. So that's the other half of the sandwich. And the top and the bottom of the sandwich have limits, 0. So as theta goes to 0, the limit of 0 is 0. And we said before that as theta goes to 0, the limit of the absolute value of theta is also 0. So the sandwich theorem applies. Say so again, can take domain -1 to 1 with 0 removed. And so we get that the limit of 1 minus cos theta is 0. And now we get a good exercise in using our limit laws, that the limit of a difference of functions, in this case 1 and cos theta, is the difference of the limits. And the limit of the constant function 1 is just 1. And the limit of cos theta is what it is. But this calculation tells us that the limit of cos theta must be 1. And that's what you'd expect, again, from looking at the graph, that as theta gets smaller, cos theta gets closer and closer to 1. But the point of doing exercises like this is it's not always so easy to see what a limit is going to be. And so we're developing these tools to let us calculate more difficult limits, you will see. So a theorem which is related to the sandwich theorem. It's saying that if I have functions f and g in the same situation of a domain an interval a to b with a point c removed, then if I have two functions fx and gx, and f is the smaller, so this is fx, and this is gx. Then if the limits exist at c, then the limit of f is less than or equal to the limit of g. So I'm going to draw in another example. Let me make a bit more space. Yeah, let me just modify this one. So notice the condition is that f is less or equal to g for all x in the domain But we could have something like well, that graph looks a bit silly, but the idea is that f and g can be equal, and they can be approaching the same value at c. And so in that case, the limits could be the same. And that's shown by this less than or equal sign here. So this seems to be related to the sandwich theorem, but we have to be careful. In the comparison theorem, we assume both limits exist. But remember, in the sandwich theorem, the theorem let us conclude that the limit of f exists, just because we knew that the limits of g and h existed and we knew something else. So this note is about that. If we assume the assumptions of the sandwich theorem, so the thing we started with, that g is less than f is less than h, and if we also assume that the limit of f exists, then the comparison theorem gives us the conclusion of the sandwich theorem. That is that the limit of fx must be L. So why is that? Well, because if we assume everything on the top half of the screen, then we have that L is the limit of gx, and the comparison theorem gives us that that is less than or equal to the limit of fx, and it also gives us that it is less than or equal to the limit of hx. But we've assumed that equals L as well. So the only possibility is that the limit of fx is equal to L. So that's just to explain how they're related. And to give an example, in this case, one of the functions is 0. So this is the case when fx is always 0. So then the inequality reads that gx is greater than or equal to 0 for all x in the domain. I've chosen it to be -1 to 1, with 0 removed again. And then if the limit of gx exists, the limit of 0 certainly exists, it's 0. And so the comparison theorem gives us this. And of course, we're using again the limit of 0 is 0. So in the picture, if gx is positive above the x-axis, then whatever the limit is, it must also be positive and greater than or equal to 0. Okay, so let's stop there and take a break. Let me know if there's any questions. Okay, so I can't hear the class bell, but I think it's time to start. Okay. So there was a question, what does this set here mean? So it's the open interval -1 to 1 with 0 removed. So I can draw it like this on the number line. Okay, but if I'm going to draw it like that, I need to make clear that the function gx it only has values between -1 and +1, excluding -1 and +1. Okay. So a question, why don't we need the limit of fx to exist in the sandwich theorem, but when we deduce the sandwich theorem from the comparison theorem? So we do need the limit of fx to exist to deduce the sandwich theorem from the comparison theorem. That's my point. So it's an easy mistake to make to think that you don't need the limit to exist, but we do need the limit to exist. Thank you. Okay, so let's continue. So we started with the sandwich theorem holds for less than and also for less than or equal. But this is not true for the comparison theorem, so we have to be careful. So what I'm saying is, in the comparison theorem, it's always less than or equal. If it was less than, so let me copy the comparison theorem. So here's the comparison theorem here. So the point I want to make is that if I replace less than or equal to with less than, an easy mistake to make, this theorem is not true anymore. So, not true. And why is that? Well, take this example, gx equals x squared. Then, on the domain, -1 to +1 with 0 removes, on that domain, gx is greater than 0. So if this version of the sandwich theorem was true, then we could put f equals 0 and take this gx. And we could get this relation between the limits. But in this case, this is not true. So the limit of gx is not greater than 0. In fact, it's equal to 0. So we can see that from the picture, and we can see it from the limit laws. But this is quite a subtle example because we had to take the domain -1 with 0 removed. So if 0 was in the domain, then of course it would not be true that gx is always greater than 0. Gx could be 0. Okay, so thanks for the questions. So question, Benjamin Lee. For the sandwich theorem, replacing less than with less than or equal to is a weaker but still correct definition. Yes, that's correct. So replacing, have to get it the right way around. So replacing less than or equal to with less than just a moment. So less than is more information. So it makes it easier to prove the theorem. Replacing less than with less than or equal is a stronger theorem. So why did we take up point C while discussing the sandwich theorem? So this is an example where it makes a difference. Because without the point C, a function might be greater than 0, but at the point C, it's equal to 0. So removing the point C and considering the limit at that point is often important. And we'll see more examples of that. This is one, but we'll see other examples. Okay, thank you. So now we're ready to precisely define a limit. So we said in words that the limit of fx as x goes to x0 is L if, as x approaches x0, the value approaches L. So let's be a bit more precise. So I wrote it out here. For an interval containing L, so you can think of L in some position on the vertical axis and some interval on the axis containing L. Now the idea is, however small that interval gets, we should be able to force fx into that interval if x is close enough to x0. So let's give a really simple example to make that clear. So I take the function fx is 2x minus 1. And I claim that the limit at x goes to 4 is 7. So this follows from the limit laws from last lecture. But let's start to see why it's true. So L for us is 7, this point on the vertical axis. And the idea is if I choose an interval containing 7, then I can force the value to be in that interval by asking for x to be close to x0. x0 is down here and it's 4. Now, let's choose our interval to be 5 to 9. So 5 at the bottom and 9 at the top. So how to force the value to be in this interval? So I mean, this is obviously a very simple question, but it's good to start simple. So equivalent to this, 7 is in the middle of the interval, so we're asking for the distance of y from 7 to be less than 2. And then we can calculate that y minus 7, using the definition of the function, is 2x minus 8. And we can take out the 2 and see that this is twice x minus 4. And so, how do we force the absolute value of y minus 7 to be less than 2? Well, if we just force the absolute value of x minus 4 to be less than 1, then the equation above implies it. So for the limit of fx to be L, what we want is to be able to make this interval on the y-axis smaller and smaller and still be able to force the value to be in that interval by forcing x to be near x0. And we said in last class that there are times when you can't do this. There are times when the limit does not exist. And we'll come back to those examples and explain in more detail. But as I say, we have to be able to make this interval smaller. So let's write it like this. Instead of y between 5 and 9, let's take y between L minus epsilon and L plus epsilon. So this epsilon that looks a bit like an E, this is the Greek letter epsilon. And this is equivalent, of course, to y minus L is less than epsilon. And now the picture becomes L equals 7 and an interval with 7 at its center. And here, and this is the convention, that epsilon is a number which we usually consider to be small. So it can be any positive number, but the idea is that we're allowed to make it very small. That's the point of the definition, that we want for very small epsilon to be able to force the value into that interval. So I just said a number that is usually considered to be small. Okay, and now we can give the precise definition of a limit. So that's so let the function f of x be defined on another one of these domains where we have points A and B and a removed point between them. Then the limit of fx as x goes to x0 is L if for all epsilon greater than 0, there exists some delta also greater than 0, such that if my x is close to x0, then fx has to be close to L. So x is close to x0. The distance of x from x0 is less than delta, forces fx to be close to L. The distance of fx from L to be less than epsilon. And the idea, as I say, is that for all epsilon, however small, there exists some delta which makes this true. Okay. And notice again, remember from last time, that the value of the function at x0 does not influence the limit. And that's reflected by this, that we don't look at x equals x0. We take x minus x0 absolute value greater than 0. In other words, x is not equal to x0. Okay. And now, so we have this definition, lots of words and symbols. Really, you have to practice with it to use it, and we'll do a bit of practice. But some remarks about which parts of the definition are important. So this domain, A to B with x0 removed, that is important, but also often our function will have domain, the real numbers, for instance. But we can shrink the domain to A to B with x0 removed. But the important thing about the definition is that the function does not need to be defined at x0. it only needs to be defined close to x0. It's important. But often, the function is defined at x0. Often it's defined on the whole of R. But the definition still works if it's not. It still works if it's just defined in a small interval near x0, and it doesn't have to be defined at x0. Okay, so as I say, if we have a function with domain R, we can make a function with any smaller domain. So we can shrink 3 to 2 to 1. And we can shrink 2 to 1. So for example, if I take fx equals 2x minus 1, then the limit as x goes to 4 is 7 in the precise definition which we gave one slide ago. And notice in this case the domain is the whole of R, but we can shrink to a smaller domain. So you could prove this example using the definition. Let's do another example. You could do the top one yourself for practice. So example, prove that the limit of 5x minus 3 as x goes to 1 is 2. So here the function is 5x minus 3. Well, what does the definition say? So if we want to prove that the limit is 2, then we have to check the following. That for each epsilon greater than 0, there exists some delta such that this line here. So for each epsilon greater than 0, we need to find a delta such that for all these x's, when the distance of x from 1 is less than delta, but not 0, so close to 1, then the value of fx is close to 2. So this might star. Fx minus 2 is less than epsilon. So of course there are an infinite number of epsilons we can choose, so we need a method for each epsilon to find a delta. And the trick is to work backwards. So let's look at this statement star, fx minus 2 less than epsilon, and try to solve that inequality. And that will let us choose a delta such that this implication is true. Yeah, got to say, so this is the Greek letter delta. Yeah, so here we have the Greek equivalent of D, and here we have the Greek equivalent of E. That might help you remember which way around this goes. So let's do this working backwards. So star, the absolute value of fx minus 2 is less than epsilon if and only if just using the definition of f of x, but only if 5x minus 3 minus 2 satisfies that. So 5x minus 5 is less than epsilon. And again, we can take out the 5 to get 5 times the absolute value of x minus 1 is less than epsilon, and then we can take out 5 to get x minus 1 is less than epsilon over 5. And so we see that if x minus 1 is less than epsilon over 5, then star is true. So we can take delta is epsilon over 5, and then we get our implication. So we only needed for the absolute value of x minus 1 less than delta and greater than 0. We have it for any absolute value less than delta. So I've said it in words. So the requirement at the top of the screen is fulfilled. For all epsilon greater than 0, we would just take delta is epsilon over 5, so the limit is as we claimed. So an important point, which can be confusing, that the choice of delta is not unique. So we could still prove that the limit exists by choosing a smaller delta. For instance, if we chose delta equals epsilon over 10, so if we asked our x to be even closer to 1, then the values would also be forced to be close enough. So you can see that by checking over the example again. So the choice of delta is not unique. We just require that some delta exists. We don't have to choose the best one or anything like that. Okay, so the same sort of argument, but simpler. We get that the limit of x as x goes to x0 is x0, which we said last time. And the limit of k, a constant, as x goes to x0 is that same constant k. So you could use that to check that the definition works. Let's try a more challenging example. So I claim that the limit of the square root of x minus 1 as x goes to 5 is 2. So we can prove this from the limit laws. The limit of x, the limit of x minus 1, the limit of the square root of that. So it's 5 minus 1 square root is 2. But let's prove it using the definition. So first I'm going to prove a bit of it. So to have a limit, we require a delta for every epsilon. Let's just find a delta for a particular epsilon. Epsilon equals 1. So certainly we'll need to be able to find a delta for that one epsilon. So epsilon equals 1. We claim there exists a delta such that if the distance of x from 5 is less than delta, but the distance is greater than 0, then the distance of the value square root of x minus 1 from 2 is less than epsilon. So how to find such a delta? Well, again, we solve the thing on the right-hand side. So last time I called this star. Solve that. So if star is true, then the square root of x minus 1 must be between 1 and 3. That's the first line. And I can take squares and get an inequality that x minus 1 must be between 1 and 9. And so x must be between 2 and 10. And you can check back and see that the arrows go both ways. So if x is between 2 and 10, then also this is true. So that's the first step in our solution. The next step is to find a delta such that if x is distance less than delta from 5, then this inequality, so the solution inequality, is true. Okay. So then you can see we want to prove this up here, that if the left-hand side is true, then star must be true. So if we can prove that if this is true, so in step 2, if that is true, then x is in the interval 2 to 10, then by step 1, star has to be true. So we can divide the problem into these 2 steps. Now let's rewrite what I said was step 2 a little. So this is rewriting A, just a label for the rewrite. So we said that the distance of x from 5 is less than delta. That's the same thing as x being in an interval 5 minus delta to 5 plus delta. And x being between 2 and 10 is the same as x being in the interval 2 to 10. And that implication here, that's the same thing as one interval being inside the other. So, oh yeah, I drew a picture of this. So the interval 5 minus delta to 5 plus delta like this is inside the interval 2 to 10. So there should be little circles on those intervals, and I'll draw those later. So now we can see on the picture, if the small interval is going to be inside the big interval, then we want to have delta like this. So delta has to be greater than 0 anyway, and for small to be inside big, delta has to be less than or equal to 3. So we can pick delta equals 1, for instance, and we're done. So this shows that for the epsilon we gave, there exists a delta. Delta equals 1. Okay, so why don't we just try this for any epsilon? Well, we can do the same thing algebraically. So we can get a delta for any epsilon greater than 0 and fully prove the limit claim. So what do we want to prove? What was the definition of a limit? Let's recall it. Given epsilon greater than 0, we want to find delta greater than 0, such that this implication I holds. So x is close to x0 implies fx is close to L. And the delta and the epsilon control how close. So following the example above, we split this into 2 steps. So remember, the first one was solve this inequality star to get an interval AB containing x0. And for the general method, this thing about the domain again, we don't have to know this is true on the whole interval. We can just do it on the interval less than x0. But again, there'll be different cases. Again, if you've done step 1, and then you can find delta such that the small interval, x0 minus delta to x0 plus delta, which is what we took above, is inside the big interval AB, then we're done by putting these 2 steps together. So combining 1 and 2, we get implication I. And that's because, again, this little interval is inside the big interval A to B. And we knew that star was true on the big interval, maybe not at x0, but everywhere else on the big interval. So it's certainly true on the small blue interval. And then we have I. Okay, so about the domain, if we can find an interval AB containing x0 such that star holds for all x in AB, then great. So we only need star to hold for x in AB with x0 removed. But if we can prove it for all x in AB, then great. So the method still works. And this will be true in our example, actually. Okay. So we could use that to prove the limits that we had in the previous example, square root of x minus 1. But I think that would be a bit boring to go through it again. So let's do a further example. If I let a function be defined x squared for all x not equal to 2, and something else for x equals 2. So I've drawn the graph here. So for most of the graph, it's x squared, but for x equals 2, we have a different value than for the function x squared. Okay. And then we want to prove that the limit of fx as x goes to 2 is still 4. So whatever value the function takes at this point 2, the limit is still going to be 4. So the value of the x squared function, even though f of x is not quite the x squared function. Different 2. So the first step, remember, is solve star. And in this case, that's fx minus 4, the distance of the value fx from the limit 4, that we want is less than epsilon. So we solve that. But that's not so easy because the definition of fx is a bit complicated. So let's first solve the simpler question for the function x squared and see if that solves the problem for us. It will. So we first solve x squared minus 4 absolute value is less than epsilon. So that's equivalent to x squared minus 4 is between minus epsilon and plus epsilon. And I can add 4, get x squared in an interval, and then I can square root, get x between 2 square roots. If both of the values are positive, of course. So we assume that epsilon is less than 4, so that 4 minus epsilon is positive. And 4 plus epsilon is certainly positive, and it's even larger because epsilon is positive always. So here we can assume this, and I explain why this is all right at the end. So we just leave that for now. But you shouldn't be too surprised because I said you want to think of epsilon as a small number. So the small epsilons are the important ones. We'll come back to that at the end. Okay. So we solved x squared minus 4 is less than epsilon, which is not quite what we wanted. We wanted to solve star. But fx equals x squared for x not equal to 2. So we actually have solved star. We've solved star for x in this interval, as long as 2 is removed. So this is the kind of case where it's important to know if x0, in this case 2, is in your domain or not. You have to be careful. So we've solved star for that domain. And step 2 was to find delta such that small interval on the left is inside big interval. And we can always hope to do that because we can choose delta as small as we like. So what can we take in this case? We can take the minimum of 2 minus square root of 4 minus epsilon and square root of 4 plus epsilon minus 2. So if you draw a picture, you'll see so if this is 2, and this is square root of 4 minus epsilon, and this is square root of 4 plus epsilon, then the two things in this min are these distances. This distance. And if I choose delta to be the smallest one of them, the min here means take the smaller number, then the small interval is going to be in the big interval. Okay, so putting 1 and 2 together, we are done for epsilon greater than 4. But how about bigger epsilon? Well, all we need to say is this. So we found for any epsilon less than 4, some delta. So for instance, for epsilon equals 2, we found some delta. Well, if epsilon then is bigger, then the same delta is going to do the job. So it's saying that if a certain delta forces the value to be within epsilon of the limit, and epsilon is 2, then if I want to force it to be within 4 of the limit, I can take the same delta. Same with any larger epsilon. So this logic always works. If the delta works for a particular epsilon, then the same delta is going to work for a bigger epsilon. So after that, we are done for all epsilon greater than 0. Okay, and again, this note, in the same way as before, I'm sorry, we should be taking a break now. So I still can't hear the class bell. So let's take a 5-minute break, even though we're a bit later than planned. Okay. Okay, let's continue. So before the break, I was saying there is not a unique delta. If some delta works, then a smaller delta will work. But also, we just need to know that some delta exists. We don't need to say what it is. For instance, in this case, we just need to say, take the smaller one of the yellow and the blue, whichever one it is. We don't have to work out which one is smaller. We only need to check that some delta exists. Okay, so now we start to see why it's important to build this theory. And that's because many limits are hard to calculate. So the limit laws allow us to calculate limits in lots of cases. We saw last time polynomials, quotients of polynomials. And we use this theorem. So assume we have functions fx and gx, and the limits are L and M. And M is not 0, then the limit of the quotient, fx over gx, is the quotient of the limits, L over M. So you might think that if this theorem doesn't work, then the limit does not exist, but that's not true. There are many cases where the limit exists, even though the theorem doesn't work. So let's take the function sine theta over theta. So the natural domain for that function is r with 0 removed, because sine theta is defined for any r, and we can't divide by 0. So the natural domain is r with 0 removed. So we have a function f from r with 0 removed to r, given by sine theta over theta. And so we can ask, does the limit as theta goes to 0 exist? So for now, I just want to calculate some values, and you could do this too. And I'm using a spreadsheet. Let's start with pi over 2. At pi over 2, remember sine is 1. So the value is 2 over pi. And this is 2 over pi to 3 decimal places. And then I just halve that. So I get pi over 4. And I calculate the value. It's 0.900, etc. And then halve it again, I get 0.97 something, 0.99 something, 0.99 something even closer to 1. So it looks like the limit is 1. But how would you prove this? So it doesn't follow from the limit laws, because the limit of theta as theta goes to 0 is 0. You can't divide by 0. But we'll see how you can calculate that limit. And so when you draw the graph, you see where the limit is 1. Okay. But we'll come back to that. So now let's use our precise definition of limit to prove one of the limit laws. So you probably believed the limit law when you saw it last time. Just matches up with the graphs you draw, but this is a proof. And we use an inequality so this is sometimes known as the triangle inequality. So the vectors on the sides of a triangle are A and B and A plus B. And the length of the A plus B side is less than some of the lengths of the other sides. And this inequality is a bit like that, except we're just taking A, B are not vectors. But still, the same sign, meaning the absolute value, we get this inequality. And to check this, we just have to take AB positive. Then it's obvious because A plus B equals A plus B. But then if I make one of A and B negative, it's still true. And the same if I make them both negative. So there are 4 possibilities. And you can check. Okay, so the limit law I want to prove is that if I know the limits of f and g, and they're L and M, then the limit of the sum is L plus M. So we saw examples of this being true. But now we can prove it using our precise definition of the limit. So suppose given epsilon greater than 0, we require delta greater than 0 such that for x, if the distance of x from x0 is less than delta, but greater than 0, then this is true. So it's a bit more complicated now. We want the difference of fx plus gx from L plus M to be less than epsilon. So that's what we're trying to prove. And we assume the limit L of fx and the limit M of gx. So how can we use that assumption to prove what we want? So this long inequality, let's look at LHS, the left-hand side. That inequality. So I want to say something about that. And that will be the secret to our proof. So the left-hand side, if I just rearrange, is equal to this. So I've just gathered F and L and G and M. And then the triangle inequality gives us that absolute value. So I've got absolute value signs here. That absolute value is less than the sum of 2 absolute values, fx minus L and gx minus M. And from the definition of a limit, we know something about those 2 absolute values. So what do we know? Well, because the limit of fx as x goes to x0 is L, then there exists delta, and there's going to be two deltas, so I'm calling this one delta 1. There exists delta 1 greater than 0, such that for all x, if the distance of x from x0 is less than delta 1 but greater than 0, then this thing, star L. So this is like the stars we saw before, with one difference, that we take epsilon over 2. So we'll see why we need to take that in a moment. But first, let's just say that we also exist delta 2 greater than 0, such that for all x, the same kind of statement is true but for g and m. So I call this star m. It's the distance of gx from m is less than epsilon over 2. Okay, and just to be clear, here we use the definition of the limit, but we replace epsilon with epsilon over 2. Because if the limit exists, then we have a delta for any epsilon, as long as it's positive. So if we have a delta for epsilon, we have a different delta for epsilon over 2. So we can say what we've said here, these two implications. And now that's enough to prove our theorem. We can now choose a delta. So let's choose delta to be the smaller out of delta 1 and delta 2. These delta 1 and delta 2 can be different. Then, if I choose that delta, zooming out, if I choose that delta and I take x, whose distance from x0 is less than that delta, but greater than 0, then if it's less than that delta, it's certainly less than delta 1 and delta 2. And that's what these two implications further up are designed to work with. So in that case, we get delta L and delta M. So we have two things that are less than epsilon over 2. So going back, LHS is less than or equal to the sum of two things. And now we've proved that each of those two things is less than epsilon over 2, if we choose this delta. And so LHS is less than or equal to epsilon over 2 plus epsilon over 2. And that, of course, is equal to epsilon. So if I choose this delta, the min of delta 1 and delta 2, then LHS is so I made a small mistake here. So LHS is less than epsilon over 2. Okay. So LHS is less than epsilon. Okay. And why is that? Well, it's because LHS is less than or equal to the sum of those two things. And both those things are less than epsilon over 2. So the sum is less than epsilon. Okay. And that's what we needed to show. And I guess you'll have seen it's used in the book. This square means proof is complete. So that completes the proof of the theorem. Okay. So in the same way you could prove other limit laws. So we have the sum limit law, which we just proved. We have the difference limit law. You could prove that in the same way. And after that, it gets a bit harder. So the multiplication limit law is harder than that, and the quotient law, I think, is even harder. But some of the proofs are given in the book. So it's good to take a look. Okay. So, what next? So we've used our precise definition of limits to prove that limits exist, but also sometimes limits don't exist. So we said this last time, that in these cases, A, B, and C, the limit at 0 so limit of y as x goes to 0 not exist. Okay, and we said that A doesn't have a limit because the function jumps, and B doesn't have a limit because the function gets too big, and C doesn't have a limit because the function oscillates too much. So we can now prove that this does not have a limit. Okay. Yeah, so just answering questions in chat. Shouldn't LHS be some formula? Yes, it is that formula. It is equal to that formula. We defined it to be something closely related to that formula. And it's less than or equal to the sum of two absolute values. So it's less than or equal to. It's actually equal if everything is positive. So you could check that. But sometimes one of those things in your brackets can be negative, and then it becomes a less than rather than equal. Okay, I hope that's clear. And yes, the answer to the last question is yes. Okay, and yeah. Okay, so thanks for that response. And yeah, a comment from, I think it's Jan. Why is something less than epsilon over 2 instead of epsilon? Yeah, it's just as you say, the final inequality has to be epsilon, so we put a half epsilon there. So it's a feature of these proofs that you only know what to do when you get to the end. With a bit of practice, you can look ahead and think, oh, I need to put epsilon over 2 here because at the end, epsilon will come out. I mean, for instance, if you were summing three things, you would put epsilon over 3, and then it would come out right. So, so it takes practice to get that right. So I was going to prove that the limit does not exist in case C. Okay, and because of the late start, I'm going to go through this relatively quickly. Yeah, okay. Okay, so let's prove that the limit does not exist in case C. And the method to prove that something does not exist is often to assume that it does exist, because that gives you some information to work with, and then prove that that's actually impossible. So suppose the limit does exist, then show this is impossible. So this is sometimes called by a Latin phrase, reductio ad absurdum, so reduction to absurdity, or proof by contradiction. Okay, so in this function, I'm going to write it out actually. So in this function, fx is 0 for negative x and sine 1 over x for positive x. Suppose the limit as x goes to 0 is some limit out. Suppose the limit exists. Okay, and let's look at the graph here. So you could draw this graph on a computer, but you can also see why it's like this. So as x gets closer to 0, then 1 over x gets very big very fast. So when x is 1 over 2 pi, 1 over x equals 2 pi. When x is 1 over 4 pi, x is 4 pi, and so on. So as x gets closer to 0, we see further and further parts of the sine x graph. So that's what we're seeing in the graph here. That's the graph of sine x going out to infinity is all squashed close to 0 in this graph, in sine 1 over x. And so that means that when we're close to 0, this function takes values always between 1 and -1. That's the range of the function. But very close to 0, it takes all possible values in that range. So you can see that from the graph, it's oscillating like this. And that lets us prove that no limit exists. So suppose that the limit is L. And what's the definition? For all epsilon greater than 0, there exists delta greater than 0 such that this implication holds. So if the distance of x from 0 is less than delta, then the distance of fx from L is less than epsilon. Okay, so we have some information. For any epsilon, there exists a delta. And we want to try and make a contradiction. We want to show that this is impossible. So we divide this into cases. So for instance, the case L is greater than 1. So say the limit was up here, 1.5, something like that. Well, that's sort of obviously impossible. But let's make the precise argument. Why do I say it's obvious? I mean, so the limit is some value that the function gets closer and closer to as x goes to 0. But the function is never anywhere near 1.5, its maximum is 1. So how do we prove it's impossible from the definition of the limit? Well, we take the distance from L to the top of the range. So that's L minus 1, and let's let epsilon be that. So then star says that fx minus L is less than L minus 1. So that means, in particular, that fx minus 1 is greater than minus that. So minus brackets L minus 1. And we can rearrange that inequality to get fx is greater than 1. But that's impossible because we know the range of fx is between minus 1 and 1. We can see that from the definition. So in that case, when L is greater than 1, then we can see that the limit gives a contradiction. You can see this case is impossible. And similarly, for L less than minus 1, a similar argument works. We just have to change the signs. It doesn't make any difference. So I won't write that out. I'll just say a similar argument works. But now the harder question is when L is between minus 1 and 1, for instance, where I've drawn there. And so why does the limit not exist there? So the answer is f gets close to that value. You can choose values of x which are very small, close to 0, such that f is close to that value. That's not the problem. The problem is that you can't force f to be close to that value because if I change x a little bit, the value of f changes a lot because it's oscillating a lot. So let's make that more precise now. So let's suppose that L is between minus 1 and 1. So that could include minus 1 or 1. So now I want to prove that the limit can't be this. So the trick, or at least the method I'm going to use, is the following. There are lots of ways to prove this. What I'm going to use is, it's easy to find x's such that f of x is 1 or minus 1. You'll see why. Okay, and I'm going to copy in once again the information that we have. Okay, so remember again that for all epsilon, there exists delta such that this implication that I put in a box is true. Okay, so how can we use this information? We'll choose epsilon small enough such that one of these things is true. So A is that the distance of L from 1 is not less than epsilon. And B is that the distance of L from minus 1 is not less than epsilon. So we can always choose epsilon such that one of these is true. We can't always choose epsilon such that both of these is true. So for instance, if L is equal to 1, then A cannot be true, because the left-hand side of A is always 0, and that must be less than epsilon. Similarly, if L is minus 1, then B can't be true. But if L is minus 1, then A can be true. I can choose an epsilon, and vice versa. So, but if L is inside the interval, it's not either minus 1 or 1, then I can choose an epsilon such that both of these are true, and the picture shows that. So, in the picture, the distance from 1 to L is not less than epsilon, it's bigger than epsilon. So the little interval is inside the big interval. And also, the distance from minus 1 to L is not less than epsilon, it's bigger than epsilon. Okay, so how can we use this? It's what I said, that if I let x be 1 over n plus a half times pi, for n some natural number, then we know what f of x is. So f of x by definition is sine of that natural number, n. And by this I just mean, as we said at the start of the course, 1, 2, 3. So it's the sine of one of those plus half times pi. And remember, in the graph of the sine function, that's minus 1 if n is odd, and plus 1 if n is even. So as n gets bigger, these x's get smaller and smaller and closer to 0. So that means that for any delta greater than 0, there exists x with 0 is less than the absolute value of x is less than 0. Oh, I said that wrong. 0 is less than absolute value of x is less than delta. And we know from the top that if that is true, then star should be true. But if star is true, then A can't be true. But in the same way, I could choose an x such that fx is minus 1. It's by taking n odd. And in that case, B can't be true. And that's impossible because we chose epsilon small enough such that one of A and B was true. So they can't both be false. And that shows that the limit does not exist. Okay. So that was a hard example. If you did example A, when the function jumps here, then it would be easier to show that the limit does not exist, just from the definition. Okay. All right, so let's make one more note and then we'll finish. So after that proof, so when we first said that C does not have a limit, we said it was because it oscillates too rapidly near 0. So this is a good explanation, but we have to be careful with it. If we think a function oscillates too rapidly and it doesn't have a limit, then really we have to prove that it does not have a limit, like we did just now. And the reason is that there are functions which oscillate rapidly. Let's take this example, fx. It's sine 1 over x, but times x. So it's oscillating rapidly, but as we get towards 0, the oscillations are getting very small. So actually, then the limit is equal to 0. So how to prove that? Well, we can prove it using the sandwich theorem. So this function, and this is quite easy to see because we know the range of sine 1 over x. So the range of sine x and also sine 1 over x is minus 1 to plus 1. So in this function, we're multiplying x by a number between minus 1 and plus 1. So this function is sandwiched by these g and h. So minus mod minus the absolute value of x, that gives us this, and plus the absolute value of x gives us this. So between those two things, the function is in a sandwich, and we get that the limit is 0. So the limit exists, even though it oscillates rapidly, because the oscillations get smaller. The limit exists. Okay, so that's a good place to stop a bit early. Next time we will calculate more limits, and we will get closer to calculating rate of change, which is what we really want to do. So now we're calculating limits carefully, they'll allow us to calculate rates of change and slopes and all the useful things. So thank you very much. I'm sorry again for the late start to this class. Thank you for your patience.